So, what are we doing today? We will. This like is so dope, man. I usually don't like that style a lot, but it's pretty tricky. But I'll cut down that. Or let's just. So let's go back to exercise. Let's go back to what we're doing. That's exercise. I wanna keep looking at this. There we go. So, and again, we're doing like quick sessions this week, but I prefer to just do quick sessions than doing nothing. I'd say. Roadmap, should bookmark that eventually. What I want to do is I want to do the part that I want to deep dive a bit more into the whole quantum observable stuff, and why does the quantum Fourier transform help there. That has been bugging me because that's something I don't know. So that's just another excuse probably to basically not do the maths. I know we talked about A, and it's about probably just doing an integral, right? But we are now, or I'm not going to be something. Let's put it this way. To solve this exercise, I need to understand a bit more of this whole change of basis and why does the QFT actually give me or help me move from the position space to the momentum space. So that's kind of like why is that? So let's dive into this. How can we even approach that? So relationship between position and momentum space. Why is it that the QFT actually works? Let's do Wikipedia. Wikipedia seems to be always one of the best options, to be honest, to start with. At least when I do a bit of research like that, in order to solve a problem, that's typically what helps me the most. And I think I've been doing sometimes too less commentary around why am I doing the things that I'm doing in terms of looking at that, or searching or not searching. I don't know. We'll see. By the way, maybe I just have to drop it in as like unexpectedly, keyed stuff, but whatever. It is what it is. Let's jump to this. So, position and momentum spaces. For the jazz album, see Momentum Space. Is there a jazz album, Momentum Space? I gotta listen to this Momentum Space. Let me just say YouTube.com, Momentum Space. We gotta listen to this.
Find more dates and more great deals on a huge range of refundable hotels and holidays. Book your next luxury break at secretescapes.com. At or protected.
I'll probably have to... Not a lot into jazz, but why is it so loud? I'm sorry, guys. I think it's quite loud. Yeah, I think that's going to be probably better. So it's not so much on the... I like that. Maybe I'll see how that actually sounds in reality. So you hear less of it. Maybe I might play some music in the future. Some non-copyrighted music, of course. Yeah, I don't like it. I don't like that. I definitely don't like that. This one. Got deceived. Momentum space. Not good. Anyway, let's get to the actual thing. So this is basically saying that in physics and geometry there are two closely related vector spaces. So this is something that. But why are they closely related, right? And why is the relationship the QFT kind of? So position space is the set of all position vectors in R. So R is a position vector. That is something that has been confusing me a lot in the exercises. They used R, the R notation, and I always like it's radius or whatever. It's an actual position vector. It has a dimension and length. And has dimensions of length. Okay, yeah, length. A position vector defines a point in space. If the position vector is a point particle varies with time, it will trace out a path, the trajectory of a particle. Momentum space is a set of all the momentum vectors that the physical system can have. It's okay. So it represents motion, right? Mass times length per time. Mass length. Okay. So mathematically, the duality between these two examples these two spaces is a Pontragine duality. Is a duality between locally compact abelian groups that allows generalizing. Okay. So there is a mathematical reason why that makes sense. Or it's not. Maybe it's just a mathematical property. It's not necessarily that there is an explanation to this. But okay, we're talking about abelian groups, which I think I remember. I don't know what they are exactly. I'll check that definition in a second. And that allows generalizing Fourier transforms to all such groups, which include the circle group, the finite abelian groups, and the additive groups of integers, the real numbers in every finite. Okay. What is an abelian group? Oh, come on. I don't want... Why am I just getting the damn language of... It's just because of location or something? An abelian group is also a commutative group, is a group in which the result of applying the group operation to two group elements does not depend on the order. So there's commutation. Okay, that's a abelian group. In particular, if a function is given in position space, then its Fourier transform obtains the function in momentum space. So that is just the definition of this duality. But why is that? Conversely, the inverse Fourier transform momentum space is position. Okay, so it's basically, this is just stated here, right? So that's, with that I could just go and solve the problem, but I'd like to go a bit beyond that. Why is position and momentum? So these quantity ideas transcend all of classical and quantum physics, and the physical is kind of both formulas and equivalent provide the same information about the system in consideration. Another quantity is useful to define the context of wave. Let's just think about this from first principles and why there is a duality to these, right? So one of these spaces is giving you positions, and this means essentially that let's try. I'm just, before I dive into that a bit more in detail, I'm trying to kind of rediscover it a bit myself, right? Because I think it always helps to understand how would you think about this, and if my keyboard will work. I've ordered a new keyboard because I'm just fed up with this one, because the machine that I'm using doesn't have USB. It has only USB-C ports, and then this damn keyboard is not really Bluetooth. Like, well, it's more like it has a receiver that it's a USB-B type or A type or whatever, and the adapter shit doesn't work well. But if I imagine, like, I have a collection of, like, position space, I'll just call it with the X, right? So it's basically, you've got a collection of points, right? Like, say A and B and C, for example, right? So these are different points the system can be in. And so you've got like a coordinate system, and maybe that's, that point and that point and that point, right? And of course, these all can be either represented with vectors to this origin, but those are points, right? And then and so if I think about the time dimension of it, right? If you think about a system, is you can describe the system as in like in what positions the system is in a given specific time, right? And so I can say, well, that is T1, that is T2, that is T3, right? But then another way that I have to describe these, I'm trying to think why, knowing the solution, knowing that the QFT is something that plays into these. Because the QFT, basically what it's saying is that it takes you from the frequency to the period domains, right? So in a way, I like to think about like, let's say you have like a fancy wave function or something like that that describes, I don't want to say the position, but it's a combination, like of course it's a combination of frequencies, right? So if you have like maybe, you know, frequency of whatever, like of 1, of 2, of 5, like you've got like a set of frequencies, you combine them together, right? So you have like the different things here, that will be like this, and that will be, I think, like that or something like that. So when you combine them, then you get like that wave, right? So in a way, these frequencies are, you could think of like, if I just try to think about like, well, this is momentum. Momentum is telling me at time T1, does momentum have direction? Because I'd say in you know, if we think about this as like as momentum, then I'd say, well, at time T1, my momentum vector is this, right? This means I'm moving with this speed, maybe the magnitude of the speed, whatever, in this direction. At T2, I'm moving like that, and at T3, I'm moving like that. So that's all that you need to describe the time, right? Because if you say, well, my initial position is this, and at T0, my momentum vector is like that, then where will I be in T1? So in a way, I have like, you know, what's my position at T1, right? I have these, so I could calculate how is that moving, versus with these, I can just say, well, I can calculate out of the position, I can calculate the momentum, because I can, if I know the points I am in each respective time, I know what is the momentum has got to be, because the momentum is the dynamic part of the system. So in a way, if I combine all these, yeah, one could interpret these things as frequencies, right? Because I'm like at T1, I'm, you know, that's my frequency. That's kind of how I tick. That's my dynamic. But I'm not so sure. I don't know how to think about the the frequency is just that number. It's telling you something about that, and then you combine it and you get the wave, right? So just forget about this wave. That's confusing me a bit, but it's like you've got frequencies and you combine them. But how do you go from quantities in physics describe positions of particles? Yeah, they provide the same information about the system. Another quantity is useful to define in the context of waves. The wave vector. Okay. The wave vector k, or simply k vector, has dimensions of reciprocal length, making it an analog of angular frequency. I like the smiley face, which has dimensions of reciprocal time. The set of all wave vectors in K space. Usually R is more intuitive and simpler than K, although the converse can also be true. Oh, look at this. Actually, this is probably something to do with the solution to our problem, right? Because it says that proof that the particle momentum is h bar times k. So the broccoli, the Broglie relations. Wavelength. Okay, this is going to be an interesting one to research, to be honest, because I'm already lost. Maybe the solution is in this thing here. So Pontragine duality is a duality between locally compact abelian groups that allows generalizing Fourier transform to all such groups, which include the circle group. The magnetic dual of a locally compact abelian group is a locally compact abelian topological group formed by the continuous group homomorphisms from the group of the circle group to the circle group with the operations of pointwise multiplication and the topology of uniform convergence and compact sets. God. The Fourier inversion theorem is a special case of this theorem. In mathematics, the Fourier inversion theorem says that for many types of functions, it is possible to recover a function from its Fourier transform. Fourier inversion theorem says that for many types of functions, it is possible to recover a function from its Fourier transform. Intuitively, it may be viewed as the statement that if we know all frequency and phase information about a wave, then we may reconstruct the original wave precisely. It's good. It's actually good that the exercise taps into that, because essentially that seems so random in terms of like, oh yeah, the Fourier transform is like, but why is that so key and important with all these topics, right? And why can these so neatly be used in many situations? So a Fourier transform is a mathematical transform that decomposes functions depending on space or time into functions depending on frequency or temporal frequency. I mean, that kind of makes... So what I'm trying to do right now is I'm trying to kind of find a point to anchor my research and then kind of go up from there, right? To try to build up that knowledge from the core, from the sort of the foundations, right? Because otherwise you just go and get lost easily. So the Fourier transform is a transform that basically what it does is it takes a function that depends on space or time, but why? I mean, that doesn't really, you just take a function and then spatial frequency or temporal frequency. So it's about periodic stuff, right? So yeah. Okay, so this is a basic thing. So we're talking about stuff that repeats. We're talking about periodicity. We're talking about functions that repeat or that have some sort of pattern or may have some sort of pattern. So we're not talking about functions like an exponential maybe, or like a, you know, whatever else I can't come up with now. But, and so what the Fourier transform does is basically it decomposes that function into its frequency, or into its set of frequencies, right? Yeah. The Fourier inversion theorem basically says that you can invert that process. So if we know the frequency and phase information about a wave, then we can construct the original wave precisely. Yeah. And then I came to that from here. Saying that the Pontragine duality is a duality between locally compact abelian groups. So locally compact abelian groups are abelian groups which have a particularly convenient topology in them. For example, the group of integers. Why locally compact? Equipped with a discrete topology, circle. Why? If the underlying topological space is locally compact and Hausdorff, the topological group is called abelian. It says locally compact if, roughly speaking, each small portion of the space looks like a small portion of a compact space. Okay, I guess what it means maybe is that it's like, it's a space that if you've got some notion of dimension or subspaces and whatnot, it's like any kind of subspace you make has a similar, like a compact neighborhood. It's like, you know, that there's no like spaces between, or there's a lot of, like, if you have a notion of distance in a way, that things are not far away from each other, right? So if you take the real numbers or whatever the integer numbers, so you have like 1, 2, 3, 4, 5, right? Even, or just the natural numbers, but you have these, and it's like, well, if you pick a number, an element of the set, then it's got like 2 neighbors, right? And every one element of the set of this group, I guess, has 2 neighbors. So that's why it's locally compact. But okay, I think so. It's so easy to get lost into that. I'd love to know more about many of these, but let's try to get pragmatic. So, and we might iterate on these, but basically, so this duality is duality between locally compact abelian groups that allows which include circle group. From the group to the circle group with the operation of pointwise multiplication and topology. Any locally compact abelian group is naturally isomorphic with its bidual. Okay, but what is then this dual, right? The dual of its dual. A topological group is a locally compact group. Topological space locally abelian. Examples of the locally compact abelian group. This is so much foreign to me. It is so much foreign to me. And I came to these because of these, right? So there are two spaces that have this duality. I'll have to give another run to this, but I guess what this means is and this is the reason why the Fourier transform, it's because of the nature of these two spaces. I think that it's got to do with the fact that they are periodic. There's the periodic notion there, right? Of like, maybe not periodic, I don't know what I'm talking about, to be honest. Because this all only makes sense when you add time to this, right? So if it's two spaces, right, where you've got possible positions and possible momenta, right? And so I guess the duality between these is that they are like, you can do that, you can think of them as this. You can decompose one into the other. Maybe that's where I'm trying to get to. They have this duality. It's like you can decompose one into the other, or one of them is enough to express all the information of a system, and then you can transform between one and them because there's a composition relation in a sense. Maybe I don't know if that's what this means, right? I'm just okay, so mathematics, a duality translates concepts. So duality, it's funny because even the words like that mean something, right? It's like when we talk about like space duality, it means that there's a way to translate from one space to another. And I guess this is a kind of duality that is a composition duality or something like that. Maybe there are types of dualities. Isomorphisms, duality in projective geometry. Yeah, I guess so. Dual categories, Poincare duality. This is getting pretty abstract pretty quickly. But I guess that's it. I guess I'm so far I'm happy enough. I think I'm happy enough with the fact that like for me it's a good enough explanation that like these are two spaces that basically whenever you have two spaces that one can be made out of composing the other, like in the sense like that if you have positions, right? You have a set of positions across time. You can actually you can compose these positions to create or to derive the momentum space, right? Because you can compose these, and so you know how over time things should move, and it's a composition of these positions. I think because the QFT the Fourier transform goes from that to the frequencies, and that's how you would view these. So it's like what you're saying is you're taking the positions, right, and by composing these positions and you're decomposing these into the different momenta. Exactly. So you're decomposing, like you've got a function that says how the position is evolving through time, and you can decompose these. Like if you have multiple momentums over time, you can compose them to give you the positions the system will be in those moments in time. So the composition is, so it's a decomposition relationship from position to momentum, and it's a composition relationship from momentum to position. And this is just what these means, I guess. I guess that's what these means. I definitely can't. I'm not definitely going to go too deep into that, but I'd love to. I definitely love to spend the time on this. But it's okay. Something that I think at least has opened up my mind in terms of what is a QFT. So QFT is a transform that applies to things that compose into others, right? That's what the it decomposes functions into sort of periodical functions into compositions of frequencies, right? But I guess there are functions where this is not applicable, right? It's pretty nuts how deep you can get into these kind of things. Convolutional stuff, wow, God. Generalizations, quantum mechanics. Okay, so now I just got to figure out, this has been, yeah, I'm gonna leave it here now, but it's been, okay, so I just have to figure out how to apply this here, right? And why this is the momentum that you get in this isotropic. Not isomorphic, isotropic. I think that is isotropic. Yeah, that's what we did already in the other exercise. But yeah, pretty much that's it. Pretty much that's I think that's the trick here. So I have to understand how to do that transform, how to transform that. No, the probability density. I have to transform that into the momentum space representation, and then find the probability density. That's what I'll have to do. Yeah. Cool. That's the task for the next session. Or maybe, yeah, that's exactly, let's do that. Then we'll focus on the expectation values, R squared and whatever, and then we'll do actually the integration of these, and probably we'll just leave it there. Cool. See you next time.